All right, hi everybody. Very glad to be here. Thank you all. Thank you, Ingrid and NVIDIA, for inviting me here to speak. We've been partners with NVIDIA for, I don't know, many, many years, going back more than a decade. That started with us working very closely with them on optimizing all of our flagship desktop tools to run on their client-side hardware. And as we've turned into this Gen AI area, we now work very closely with them to really figure out how to optimize the insane task that we decided to take on of actually building our own frontier models from scratch and then serving them at scale with all of our customers to be able to provide lots of wonderful Gen AI value. So thank you guys for doing that. Okay, so let's talk about how the talk's going to go. If you're here, I'm assuming it's because you're interested in possibly building models yourself, building large-scale models, because that's really what we're going to focus on here. The relative scale of kind of where we're going to go here technically is probably middle of the road. I am, as Ingrid said, I'm CTO for Adobe, which means I know just enough about the technical depths here to really be dangerous. So I'm going to shoot for that middle of the road. If you've never done any training, you should be able to do this. If you've done some training, there's probably things in here for you to learn about what it means to do that at scale. If we do end up having time for questions and there's any, you guys want to get into the weeds, I have Marian here from our team who knows way more than I do about all of this, who'll be able to help us as well. Okay, so the way I'm going to frame this is I'm going to talk about the journey we went on, starting from why we decided to take on this crazy task of building large-scale models, how we made that decision, what the pros and cons were, and then, of course, what we learned along the way, and all the battle scars we ran into. So hopefully you guys will pick up some lessons and maybe be able to learn from them and avoid some of them when you jump in. So I'm going to jump back here first about 3 years ago. Right, so this was, I don't know, it was like late 2022. ChatGPT wasn't on the market yet. Nobody had, that mind-blowing change to the GPT world hadn't happened. But what we were seeing was a lot of media models, really starting to hit the stride of they could actually provide real value in the research labs. And, mid to late 2022 is when we saw the first models actually coming out commercially that could provide real results for end users to use. OpenAI released DALL-E 2. Stable Diffusion came along and blew everybody's mind with an open source model. And at Adobe, right, our job is taking the latest creative technology and putting it in the hands of creatives and to accelerate their craft and let them create more amazing things. And so we very quickly looked at this and said, how do we get this into our products? And we went and looked at the models out there, and we thought about what kind of features we could build. And we very quickly realized there were some problems. And the problems were, while these models were amazing and could do amazing things, they weren't going to meet the needs, the specific requirements of our customers, and so we might have to figure out how to go above and beyond that. And I'll give you two specific examples. First is control. Right? If you think back to that time, we had what we used to affectionately call prompt roulette. You type a prompt into the thing. You'd say like, "Oh, I want dogs playing poker," or some internet cat picture, and it would generate this amazing picture for you. And if you didn't like what you got, you'd change the prompt a little bit, and you get a new picture really fast. But it's probably completely different from the first picture you got. For our customers, that's a non-starter, right? These are highly trained creatives. They bring their taste and their vision, and that's as much as the technical ability, that's what they bring to the table. And so putting this technology in their hand where they couldn't iterate and control down to the fine details was not going to be useful to them. So we knew we needed models that could really push the bounds on control. The other one was really important, turns out, we found as soon as we started talking to customers, especially our large enterprises, which was all of the legal and ethical and regulatory questions about these models. Now, again, if you think back there, there was a lot of public discussion going on about the, some would say, dumpster fire of concerns around where these models were trained, where the data was taken from, what rights do people have to train on it. Are you going to get in trouble for using a model that took data from some website? Are you going to get in trouble for using a model that can completely mimic the style of a well-known artist? Do you own the content that you're putting out there? Are you going to suddenly get shut down in Europe because you're using this stuff? Every one of our customers basically was telling us they couldn't touch this stuff with a 10-foot pole. Not that they didn't want to, but their legal department was saying no way. And so we had to figure out how can we actually make this stuff available in a way that they feel comfortable adopting to get moving with. And that really came down to us going all the way back to the beginning, starting with a licensed, clean data set that we verified with human moderation, had no copyright in it, no IP that was going to get somebody in trouble. We could trace the provenance of every asset that we use to train on, and we could give that to our customers with very high guarantees that, don't worry, this is safe to use, right? So that stuff was critical, right? And we knew this was what the market needed, and we also knew it was a place we could differentiate. But that put us in a difficult position, and it's one that, if you're in the tech industry, you faced many times a year probably, which is basically build it or buy it, right? We could grab these off-the-shelf models, which were these marvels of technical wizardry and large amounts of manpower and dollars going into building them, and we could hit the ground running, but it wouldn't really meet our customers' needs, right? We'd be a lot of compromises, and it would compromise who could actually use it. Or we could roll up our sleeves and dive in and say, we're going to build it ourselves. We had access to a lot of licensed data, so we knew we could do that. We had brilliant people. Adobe we have a research team of over 200 PhDs who have been doing world-class leading computer vision research and AI research for over a decade. So we thought we knew how to do it. It was just a question if we wanted to take it on. And this is obviously the first question for you to ask. As a technologist, I always like to build things. But for something of this scale, with this level of investment, really have to take a step back and ask, what is the benefit that we think we're going to get from this? Is what we can build with this differentiated from what we can get off the shelf? And does that differentiation justify the investment that we're going to have to put into it? And that investment is large, as you'll see in a minute. So we did that calculation, and we said, yep, definitely important. We think we should do it. We think, how hard could it be? Right? Actually, and this was a little naive of us, the answer is actually not that hard. Like I said, we have very smart people at Adobe. We'd been doing AI in a while, and so we knew how to train models. This was just kind of like throwing a couple more GPUs at it, right? So let's talk about how that works. The basic idea here is, again, if you've trained a model on your laptop, it's really no different from what you've done. This is a picture of a typical training loop, right? Simple, but in some ways it is this simple, at least from the 10,000-foot view. What you do is you go gather a bunch of data, and you set up this loop, and you get a GPU, and you say, okay, I'm going to load the data off disk, and then I'm going to do some prep work. I'm going to figure out how do I transform the data so that it's consumable by the GPU. And then once I get it there, I need to turn it into something that is consumable by the model, right? I have to turn it into an embedding. And then I hand it off to the model, and I say, okay, great. Process this, look at what you did, figure out how far you're off, make an adjustment to the model so it's a little bit closer to the right answer, and then just repeat that thousands or millions or hundreds of millions of times, and you've got a nicely trained model. And then every once in a while, just to be safe, just like you do with anything you're doing, you check it back in. GitHub, save a copy on your Mac, whatever it is. We take checkpoints every once in a while along the way, and we just grab the model as it is, and we say, okay, we're going to put that back in storage, so if something goes wrong, and things go wrong all the time for all sorts of reasons, this is as much an art as a science, we can always go back to one of those checkpoints and pick up again and try going a different direction, right? So that was the basic model. Again, this is what you do in your laptop. This is what we were going to do in the cloud. We just needed a few more GPUs, and so we said, great, let's go ahead and get to work and do it. So we built a very basic training stack, right? A little bit more complicated than what you did doing your laptop because we had to do a couple things to do this. So first of all, we went and got a couple thousand high-end machines that had the best and brightest, latest NVIDIA GPUs in them. I think they were A100s at the time. I don't remember. And then we got some storage. We had our data. And the data, in this case, we had petabytes of data, and it's growing all the time. Mix of images and videos and other assets, low res, high res, long videos, short videos, different codecs and formats. So we had all this data. We needed to put it somewhere. So we used a relatively standard distributed, storage infrastructure on our provider at the time was AWS. So we, just used some of their infrastructure S3 to put our data up there. And then we grabbed some Python code to glue it together and run that loop. Let me talk about that Python code for a second. If you've done training, you know what PyTorch is. For those of you who haven't, this is the kind of one of the industry standards of how you write, complex model manipulation and training code to run on the GPU, so you don't have to get deep into the weeds. It's great. It's a very powerful library. Even that, we said, we don't think we need all that power. There's this library that exists called PyTorch Lightning, which is sort of a level up above PyTorch that says, hey, if you're going to do a standard training loop, That's easy. Just use this. We'll take care of all the boilerplate code for you, and we'll you can just kind of hit a button and get it going. So he said, great. That sounds like what we're doing. Set up that loop with PyTorch Lightning, and we were about ready to get go. We did have to make one decision at this point, which was, okay, we got petabytes of data. We got thousands of GPUs. We have to figure out somehow how do we slice up that data, or how do we slice up the GPUs to take advantage of the fact that it's not just one, but all these guys are going to hopefully accelerate training by working together. There's a lot of decisions you can make here. We took the most straightforward one. We used something called data parallelism. What that basically is we take our, so let's say we had 1,000 GPUs. We take our petabytes of data and we divide it up into 1,000 chunks. And we ship each one of those off to a GPU with a copy of the model. We have it do its training run, and once it's been through all the data and it's updated the model, we have another machine which collects all those changes back together, collates the results, takes all the work they did and figures out how to merge it, and great, now we have a new checkpoint. Fantastic. Okay, so we did this, we set it up, we got it running, and in a very short time, we actually had a model. And it was a great model, and this was our first breakthrough of like, oh my God, this is not rocket science, right? It is rocket science, but we had rocket scientists, and we could do this, right? We had a model that could create images, from a simple prompt. This was 2022, so yeah, sure, the people had 7 fingers and all that kind of stuff, but that was the state of the art of the time, and we were pretty excited about it. But 7 fingers isn't really going to work for us, so we knew we had to get better, and we had to get larger, and we had to invest to make this thing better. We were ready to do that, but we noticed a problem. And the problem was that we were not getting anywhere near as much return on the investment of those GPUs as we thought we should have been. We worked very closely with NVIDIA. We know how powerful these things were. That's not what we were seeing. And if we were going to pour millions more dollars into building up our fleet and building this thing out and going much bigger with our training runs, we had to solve this problem. So we whipped out our profiler, and we started looking at the GPUs. And we saw something disturbing. And let me show you an example here. So what you're looking at is a simplified version of what our profiler shows us. This is 2 different GPUs that we're looking at. The top one is sort of one of the standard training GPUs. So we got 1,000 of these running, whatever it is, and they're all sitting there taking their data and processing and updating the model and running as hard as they can. And all those nice colored lines, that is evidence of the GPU thinking hard and doing all this amazing work that that none of us can imagine even how it works except the rocket scientists at NVIDIA. The bottom line is a different GPU. That's kind of a special manager machine. And I said earlier, the way this training at scale works is all the machines do their work, and then there's a sort of a manager that does this gather phase where it collects all the updated models back and it collates them together. It's like the end of a test where like you finish your exam and your teacher says, okay, go take 5, go have a coffee, a cigarette, something. I'm gonna grade and get back to you guys, right? Just to pull them together, balance everybody out against each other, curve the grades, etc. And you'll notice something, which those blocks of work that bottom GPU is doing line up very well with that big blank section in the top one. That blank section is really big. It's about, if this is time, that's about 2/3 of the time the GPU could be working. It's sitting there smoking a cigarette doing nothing. Because that manager has to do a lot of work, right? The job of that manager, taking all of those models and bringing them back together and doing that merging, that turns out to be really hard and expensive. And the more GPUs you have, the harder and more expensive it gets. So that was a big problem, right? If we were putting $1 million into training, that was $600,000 that we were burning away on those GPUs sitting and doing nothing. Right, so we were getting 1/3 of the return on that that we needed. That is a big problem. It's a big problem, for our ability to get the results we want. It's certainly a big problem when I go in front of our board and explain to them why they have to spend a lot of money on doing this. Like telling them we're getting 30 cents in the dollar is not a fun conversation. So we had to fix this. And so we, again, smart people, we rolled up our sleeves, we dug in to figure out the problems were. The problem is this is only one example. This problem with data parallelism. And by the way, this example is real. I think my rocket scientists tell me these days that if you're going to do a training run with more than 16 GPUs running in parallel, data parallelism is going to run into these kind of problems. So nice, naive approach. We had to do something better. And there were many, many other places when we look around that entire training loop where we were seeing bottlenecks left and right. So we've got this distributed storage. Loading petabytes out of data over the network, petabytes of data out of memory, that takes a long time, and your GPUs are sitting doing nothing. Saving that big giant checkpoint, that huge model, billions of parameters back into storage, again, huge times loading it, saving it back in. Against, this is really insurance. Like most of the checkpoints we'll never need, and so all this time is being spent just in case, and those GPUs are sitting idle. In that core loop, right, taking all that data and then loading it up, there's actually a lot of bottlenecks in there. So just preparing the data for use on the GPU, right, that's all CPU work, and there's memory bottlenecks there that prevent the machines from running fast enough. Getting into there and loading up and using your VRAM effectively, using your compute effectively, lots of bottlenecks in there as well. Really interesting one there. These GPUs, not only are they waiting for that manager at the end, like I showed, they're actually waiting for each other as well, which shouldn't happen because they're running fairly independently. That's the whole point of working at scale. But let's go back to that not very good teacher test example. A lot of you guys are probably the smartest people in your classes. Test would come along and you'd do it and you'd finish in 10 minutes. And what do you do then? You sit around for the next 50 minutes waiting for the slowest kid in the class to finish before the teacher says, okay, everybody can get up and go and collects the test. That's exactly what happens with these GPUs. So remember, our data is very heterogeneous, right? We had videos, images, small res, high res. We had some that had very expensive codecs that took a lot of work to process, some which were just raw data that didn't take any processing. And so we were naively slicing up our data in a way that meant we could not predict in any way, shape, or form, or we weren't predicting how much time each GPU was going to take. Some of them would go really fast, and some of them, because they got the hard work, right? They were the unlucky guys who got the big, expensive movies. They would take way longer than the average because that's the way our data kind of fell out. So across all of these places, we realized, hey, just doing that kind of out-of-the-box thing where we grab some nice libraries off the shelf and we kind of throw them together and create this loop, it wasn't going to work, right? We were not going to be able to scale our usage enough to really be able to justify all the money that we're spending on doing this, even though we knew there was a pot at the end of the rainbow there that we really were going to create something different that was going to be meaningful for our customers. Hey, I lost my speaker notes monitor. I don't know if something's going on there. I will charge ahead, but who knows what I'm going to say at this point. Okay, while they're working on that. So again, this was an investment for us, and it was a big investment of time and learning and technology. We had to build a bunch of things ourselves. We had people who really had to get a crash course in this stuff. So this is another check in sort of where our training loop evolved to. Same basic structure you saw here, but there's a bunch of accelerations and sort of deeper decisions and optimizations we put in. I'll touch on a few of them. Look at the top left and right. Loading data out of memory and storing it back, out of storage and storing it back into storage. Loading it out, okay, that was theoretically not that hard. We just created a specialized balanced data loader, which instead of blindly slicing up our data, it actually, we built knowledge into it of what the data was, what the cost of the different data was, what kind of processing was needed. And we actually built an algorithm that sort of predicted, okay, how much, how do these inputs affect the workload that a GPU is going to do, and tried to balance it to figure out how we can leverage that out so the work is distributed pretty evenly between them. On the storing side, like I said, we were storing this big completed model, every 5 training runs or something. I forget the exact number. And most of that we will never use again. It's insurance. And so it's kind of a shame that we're doing all that. And our team had the bright idea of, rather than storing a beautiful completed model that an end user could use, even though we were never going to do that, we could store actually some of the pieces earlier in the process, some of the data coming off those individual GPUs. If we store that back into the distributed storage, we can take advantage of the parallelism of the storage and sort of save it a lot faster. Yeah, if we had to go back to a checkpoint, it would slow down because we'd have to rebuild the model from those pieces. But that happens rarely. That we can defer that work until it's needed, if it's ever needed. In the middle here, you see it says FSDP plus TP. This is our new parallelism approach. It stands for fully sharded data parallelism and tensor parallelism. Interesting topics there. Go read about them if you want. The long and the short of them is, rather than just slicing up the data and giving a complete copy of the model to every GPU, we can actually slice up essentially the model itself. Various directions, slice it up by layers, slice it up by quadrant, again, sort of read up for the details. But And then we hand data and just a piece of the model off to every one of our 1,000 GPUs. And what that means is the GPUs, I think, end up doing a little bit of work. I'm actually not sure. But more importantly, the act of collecting those and gluing them back together is way, way simpler. It's like working on a puzzle with somebody. If you're all trying to work on every other piece of the puzzle and then you got to merge them, that's going to take forever. But if you carve it up into blocks and you say, you work on that piece and I'll work on this piece, it's just an easy job of gluing them back together. So huge improvement on the performance of that gather step by being more advanced about how we slice up our data and then how we slice up the model for distributing among these. A couple other things, actually, I didn't talk about this in the previous one, but if you look in the lower right there, it says EFA. Our first version of the training loop ran on standard machines, standard Ethernet on the backbone, which was wonderful, except you're shipping petabytes of data around between thousands of GPUs, millions and millions of times, and that network speed becomes really, really important. Turns out Ethernet is not really up to the task of what we were doing. And so there are fantastic technologies out there that are evolutions of the adapter and the networking stack that are very, very high performant and designed for these kinds of use cases. NVIDIA has one called NVLink, which is a fantastic piece of technology. Because we were running in AWS, they had standardized on a different one called EFA, so we plugged that in, and that was a huge bottleneck we removed. In the middle here, you see it's not PyTorch Lightning anymore. Now it says PyTorch. Again, the off-the-shelf libraries are great if that's what you need, but if you need off-the-shelf, if you're going to do with off-the-shelf libraries, there's a good chance there's actually a model out there that you should be using rather than just using libraries and building it from scratch. So probably you're going to have to go a click down if you're going to actually build this yourself. And so we had to go down and learn the intricacies of PyTorch, which we knew. Again, we were using it for other things, and really optimize the actual training process itself. And we did that. This is where we paired up with NVIDIA, and we spent a lot of time really looking at how each operation that we were running runs exactly on the GPUs we were using, and just tune the hell out of those things within an inch of their life. We break that up into two buckets. A bunch of the stuff we did with them is stuff that could be generalized to other use cases, and so our friends at NVIDIA pulled those back and put them back in their CUDA and N library. I think I'm pronouncing it right, which is the library that essentially implements these operations on their GPUs. And so those are all now part of the libraries, I think, for everybody to benefit from. And there were definitely some that were very specific to our use case and our training loop. And so we were also writing custom kernels there to be able to just find the right optimizations for what we were doing. One last optimization I'll talk about. Thousands of GPUs, I don't know how many hard drives running up there. These are all high-end consumer-grade machines, right? They've got these beefy chips in front of them, but a lot of the components are the kinds of things that we're running on our desktops. When you get thousands of those running at full speed, full heat, 24 hours a day, both hard drives and machines, things are going to fail, guaranteed. And they're going to fail a lot. Right? If you're running your machine at home, maybe, I don't know how many people have actually had hardware failure. Probably not a lot of people on your desktop machine. But if we, figured out what the odds are and then we multiplied it by thousands, you're going to get multiple failures a week, sometimes a day. And you have to account for that. The first platform we built, we'd send it off. We'd say, great, here's all your machines. Assume it's a perfect world. Go run. And Friday afternoon, we'd kick off a training run. Go home, have a nice weekend, come back on Monday and find out that a network card failed or a hard drive failed Friday evening at 7 p.m., corrupted the data or hung the entire process, and no work had gotten done the entire weekend. So, if you're doing small-scale stuff, not a big deal, okay, bummer, you restart it, you go walk away for a few hours. But when you're, again, wasting or using all this money on all this, fantastic hardware 24/7, those gaps are incredibly important because you lose a lot of time, especially because it corrupted the run and then we had to go back to a checkpoint and literally kick the machine and start it again. So this wasn't rocket science, but it was work we had to do, which was build in resiliency into the code monitoring that training loop as well. So first thing we did was just watch to see if something went wrong. If we got a corrupted checkpoint or if something failed in the thing, we could automatically go back, roll back to the most recent checkpoint, load it up, and start the thing again. So You may lose some time, over the weekend when it fails at Friday at 7, but at least it restarted. You didn't have to keep checking on it every moment, from wherever you were. Second thing we did was we actually made the training infrastructure much smarter about detecting not only when the whole process went wrong, but when individual machines went wrong. So we looked at what the most common failures were. We wrote detection code for those and got it to the point where actually it could discover individual machines or individual pieces of the data that was getting corrupted, kick them out of the training run, and keep it going without any loss of work at all. Because even with that restarting, we still found it was rolling back and restarting many, many times a day, losing a lot of time just for having to roll back to checkpoints. Okay, so lots of innovations here, lots of hard work. Monitor's still down, by the way. I think I'm doing fine, but just so you know. I'm revealing all sorts of secrets here that I didn't mean to. But anyway, we did all this work. It was, this was months and in some cases years of work that we did, but it paid off, building and evolving this infrastructure. So if we look at our profiler again, you see at the top, that's what I showed you before. Bottom is where it got to. I don't remember when this was from, maybe a year later, that kind of thing. But look at that beautiful, chaotic LSD rainbow going on down there, right? That GPU is just running almost full tilt. It's probably running about 80% there, which is actually really the maximum you want it to run at. Going above that is hard to do, and queuing theory tells you there's all sorts of reasons why that's a bad idea. So that's running at essentially as fast as we want it to. And you see down below that manager GPU, it's doing all the work, bringing it together. And we've actually got some optimizations there where we said, okay, we also figured out how to make the fleet of training GPUs continue to run ahead of the manager GPU. So very little time lost. At this point, we had a training platform that we were very, very proud of, and we could go to the races and start to really invest in just being the bleeding edge of the models and what we were developing and the capabilities we wanted. And this worked, right? It's been 3 years now. We've been doing this for a while. The industry has not stood still, right? NVIDIA has released, the H100, the H200, now the B series, like amazing advancements in the hardware, which is wonderful, and we love to switch and take advantage of those, which just speeds everything up at the bottom. The problem is, as fast as our friends have been able to release that hardware, the software side is going faster. Right? The industry is voracious. The bitter lesson tells us if we just dump more data on it, dump more compute on it, we'll be able to get even more value out of it. And so we got something like this, right? That orange line is the hardware getting faster. The blue line is really it's in this case I think it's a function of the size of the models, right? They are getting bigger and bigger and bigger, which has huge effects on the training, huge effects on the cost, and rather than saying, okay, wait, great, we did all this optimization, now we can just leverage it and run, we have had to have a significant investment in a team that continues to evolve our platform, continues to evolve the capabilities, take advantage of new hardware, take advantage of new libraries or new techniques, change the architecture of our model to try and just keep pulling that line down so that we can get as close to the theoretical maximum of the hardware so that we're not sitting around waiting for machines to finish up so we can take another piece and run it. So it's been good work. We've done great work. And like I said, we have got a lot of value out of it. But it is an expensive proposition. And that is kind of the lesson I'm kind of instilling you here is going back to what I said earlier. Like there's lots of value in doing this if you see an opportunity to build something that is differentiated from the market, that creates opportunity for you, value for customers. But it comes with a cost, and it's an ongoing cost that honestly, right now, it's just getting bigger. So make sure you know what you're getting into. Be willing to learn the hard stuff, which everyone in this room I'm sure is. And if you can do it with the off-the-shelf stuff, absolutely do it. And by the way, training is only half the process, right? A lot of our GPUs and our money for GPUs is spent on inference as well. In fact, I think it's the bulk of it at this point. I actually don't remember where it is. But so it's just as important you optimize that too. And in this case, there's actually dual benefits. Number one is, yes, the more efficient our inference platform is, the more bang for our buck we get. But also, of course, if our inference platform is faster, that benefits our users, right? They get the results faster, they're able to move faster, and that's just more value for them, which ends up driving our business even farther. So we invested heavily here too. I'll talk a little bit about it. Roughly what it comes down to is when you do a training run, especially these large training runs, you build a very big, very sophisticated and complex model. This thing is big and huge and wonderful, but slow as a result. And so we go through various steps to try and accelerate it. First, we go through quantization. I always say it wrong, quantization, where we basically look at the data types in there, which are these very deep, thick floating point numbers, and we say, do we need all of the precision in there? Because if we can get those smaller, it'll run a lot faster on the GPU. Now, getting them smaller means loss of precision, which means loss of quality, but maybe that's okay. Right? It all depends on your use case and what you want it for. So this is a task of running experiments, doing ablations, and figuring out if we switch to this data type, what's the impact on these use cases, and just kind of narrowing in for you and your use case, what's the right balance between size, performance, and quality. Sparse attention. These models are all built on the core transformer architecture. The core innovation there is the attention head, which basically says, in an image situation, every pixel could possibly be related to every other pixel in the image, because obviously the eyes of the cat should be the same color, for example. So very expensive part of the architecture says, connect every pixel to every other pixel so they can all pay attention and together come to an agreement of what the whole thing should look like. It's fantastic. It is the core of all the AI that has come into our lives. But like I said, it's expensive. Now, the reality is, for a specific use case, you may not need all that connectivity. The upper left pixel may not really care what the lower right pixel is. And so this is another process of experimentation and finding, for our use cases, for our data types, do we need all of that attention? Can we find the ones that we don't need and start splitting them up, slicing them, zeroing them out, and every one of those you do, that's a savings of performance for the GPU. It's able to run faster. Lastly, compilation. The model that comes out, it's a generic, sort of very flexible, versatile model, can run on most GPUs out there with enough RAM, et cetera. But we knew we were running on very specific NVIDIA GPUs, and so every GPU has its own optimizations and idiosyncrasies, and if you can make that decision, you can actually optimize and compile the architecture and the structure of your model down to that specific GPU. NVIDIA makes a great tool to do this. We worked with them, and again, optimize the thing to run on the GPUs we were running on. Last thing I'll say is, don't forget bog standard traditional optimization, right? We have our Inference platform over there, which is a bunch of code that is figuring out, how to scale our GPUs and how to allocate all the things you do when you're building services and thinking about, dividing it up into services and independent scaling, et cetera. There's lots of optimization that you can do there. Okay, so lots of great work there. Hopefully that gives you a sense of the kinds of the breadth and scale of things you have to do and where you need to focus your time. We've been doing this for 3 years now. As I said before, the ecosystem has been evolving since then. When we started on this 3 years ago, everything I just showed you didn't exist in the libraries out there. There were all sorts of libraries to do this. The ones that were out in the public were designed for small-scale training, really, and all of the big training that was happening in big companies behind walls, like that stuff wasn't in the library, so we had to build it ourselves. But time has marched on. All of those tools and technologies have advanced. NVIDIA continues to up their game with their tools and their hardware. Other open source libraries are out there that have taken in a lot of the optimizations we did. Those are rolling back into the libraries. So if you were starting today, as I said, you may not have to do 80% of the things I just showed you. Right? They may be in those tools already, and that's just as we did first, grab off the shelf, try it, see what you can do. But again, if you're going to do something that is differentiated from what's in the market, if you feel the need for something that is not an off-the-shelf model, there's a good chance that these libraries don't do what you need, and that you're going to find your own bottlenecks, or you're going to find your own opportunities to optimize. So, as always, take the gift when somebody gives you. Start with these libraries, and then find those places that in order to get the value you want, you can optimize and go further. I think that's what I just said. Okay, so I think actually the main point of this is interesting, which is we invested all this time and money. We built this model that we were very excited about, and it worked, and we put it in market, and it delivered on what we wanted, and that was great. But there was another fringe benefit of taking the plunge and doing this crazy thing as well, which was not only had we built a great model for our users, we had built expertise and domain knowledge and a training platform and an inference platform. That really worked. Okay, thank you. And that was actually something that turns out we could put to use. So let me dive into our business in the 5 minutes I have and try and explain that to you. This is our stack that we came out with. We've got these models we built on the left. We brought third-party models in as well. We surfaced them up into our tools, built on our core company infrastructure. Great, this is providing a lot of value to our customers. Wonderful, but the more we talked to customers and went out there, we were talking to our enterprise customers, and we kept hearing the same question over and over again, which was, That's great, but it doesn't quite understand my brand. It doesn't quite understand my cartoon characters that we need to generate. We need to go deploy in some specific regions deep in parts of the world, and it doesn't really understand the culture there. These guys, they want to tell a cohesive story, especially these big companies, that follows their brand, shows their product, their universe well. And to do that, just as we found, the off-the-shelf models today still really aren't quite good enough for them, right? And so they need to go through a training process, not as big, a fine-tuning process, and with maybe thousands of images, hundreds of thousands of images. They need some GPUs, they need the platform, the people to do it. None of our customers are going to do, well, maybe 2% of our customers are going to do that. There's some very sophisticated companies out there doing the same thing. All the others basically had no way to do this. But we did, right? We had sunk costs in building these platforms, these infrastructures, building out this amazing workforce that knew how to use them. And we realized we could essentially offer this as a product to our customers as well. And so that's what we did. We said, in addition to the core value we provide to our users, we now offer enterprise customization. And we go to big companies, small companies, big brands, and we actually develop models for them. Same process, we said. We go to them, we understand what their needs are, and we ingest all their data, we process it, we enrich it, we figure out, is the pipeline that they need just an altered model dropped into the ones we already have, or do we need to build new pipelines for them? We go through the training process, adapt our frontier models to understand their specific concepts, and what comes out the other end is a model that they can call all their own and they can use to accelerate their workflows, et cetera, do all the great things AI can do. We call this Firefly Foundry, lots of marketing stuff on here. Please go read about it, especially if you're at a large company. This has been very successful, and it's been wonderful for us to see that we get all these extra fringe benefits from this investment we made, not only in offering a differentiated product to the market, but differentiating capabilities as well. We work with a lot of enterprises on this. We've got a lot of companies. A lot of them are big media and entertainment companies. I mostly can't talk about who they are, but we're having and have had very fruitful partnerships. I think we've said publicly that we work with Paramount, which has been a great partnership. We're working with Home Depot, we're working with Disney, so wide range of different types of companies there, and then all these other ones that I can tell you are really exciting if you could see behind the labels. So we fold that back into our platform, and now we've got this great end-to-end platform built on our NVIDIA GPUs, which for us are running in Amazon, serving up our models, other people's models, and then the custom models, all really unlocked by that really stupid decision we made 3 years ago, which is we're going to build this from scratch. And so if you're here listening to this talk, I think maybe you're wondering, should we make that same, oh, you know what? Okay, I got a minute, I'm going to show you some quick examples before I jump in here. This is an example of something we did with a customer. They wanted to be able to take a matte painting and then a sketch artist did of their characters, right, their IP, and be able to give a prompt and just generate a video for it. And so we did. And if you saw their original stuff, there's lots of ways you could interpret that sketch. This looks exactly like their IP to the point where they could put this out actually in the market in some places as real content. Another example here, that one was characters. This one is look and feel and the style. Give them the sketch, give them the starting point, and say, okay, I want this thing to bend upward. It does that. 4 more bits of eye candy. This is some open source IP that I think Blender and Netflix put out. We did a custom model on this, learned all these characters, the look and feel. This is all actual source material that you can find online. And then we generated a bunch of videos that all are, you can imagine are great content that, this is all relatively low-res stuff because it was a proof of concept, but the quality of what it can show here is absolutely within range of what many of our customers would say, awesome, that's final pixels for some use cases. Okay, so what I was saying before, the end result here, happily ever after, at least until the next big innovation comes along. If you're here asking, should we do this? Remember those basic questions, which is, there is huge value you can get out of doing custom training and building your own models. And you should absolutely take it on if you believe there's the ROI there. In order to do that, understand what it means to diverge from the stack libraries, use those. And then if you do decide to dive in, have fun, because this is really fun stuff. So I think that's it. Thank you, guys.